Hello, my name is Seongoh Park, and I'm currently working as a postdoc at Seoul University. Today I'm going to talk about the estimation of covariance matrix and its convergence rate, especially when there is missing data. You can easily find that many multivariate procedures depend on the covariance matrix and precision matrix. For example, principal component analysis, discriminant analysis, or the graphical models are such examples. In reality, to do these procedures, you have to estimate these parameters, covariance matrix and precision matrix. And you can find that many estimation procedures start from computing the sample covariance matrix. When you estimate the high-dimensional covariance matrix, banding and thresholding operators are popularly used. These are banding and thresholding operators, and you can see that they are applied to the sample covariance matrix element-wisely. As for precision matrix, there are popular methods such as graphical lasso, climb, or graphical tangent selector. Their optimization problems are given here, and you can find that each optimization problem depends on the data only through the sample covariance matrix. So we can say that the sample covariance matrix is a sufficient statistic for estimating sigma or omega. My question is, what is the counterpart of the sample covariance matrix when there is missing data? This is a spoiler, but the answer is the IPW estimator. So let me explain the IPW estimator here. Let's assume we have p-dimensional data which is subject to missing. And we use the missing indicator vector delta to denote which component is missing. If one component is missing, then the corresponding delta becomes 0. Based on these notations, we can decompose the observed sample y by the product of delta and x. Then we can define the IPW estimator by this way. Here the summation is for estimating the covariance between j and kth variable, but because of the missing, sum of n pairs are actually 0. So we have to adjust the weight by considering the number of observed samples. And we do that by multiplying the pi, the probability of j and kth variables are observed together here. Therefore, we obtain the unbiased estimator, IPW estimator. So now our question is, does the IPW estimator satisfy good properties from the sample covariance matrix? One of the good properties that the sample covariance matrix satisfies is that it has the convergence rate of square root log p over n in terms of element-wise maximum norm. So our question is, what is the rate of the IPW estimator? There have been different approaches to prove this rate, but they assumed missing happens independently across the variables. This may not be the case if you think of the longitudinal data where one patient is not followed up after some point. Or in remote sensing data, some sensors can be broken down together. And in this case, missing does not happen independently. Therefore, we consider extending the dependency between missing, and we try to prove the optimal rate of IPW estimator in this paper. So let me introduce the 3 assumptions that we used in this theorem, and they are shown in this diagram. The first assumption is about the distribution of data. We assume the sub-Gaussian distribution for them, and their reading dependency is implied by this covariance matrix. On the other side, there is a missing indicator vector delta, and we assume it follows the multivariate Bernoulli distribution. Marginally, they are all binary variables, but they are not independent here. For example, if we assume the dependency up to the second order, then this model turns into the well-known Ising model. The last assumption is about missing mechanism, and we use the missing completely at random structure. This structure makes the delta and x independent. Let me give you a few more notes about the assumptions. We do not assume any structure on sigma or omega, such as sparsity. Also, the rate is derived in non-asymptotic sense, so the sample size and dimension can go to infinity, but we don't assume any specific ratio between them. Finally, we assume two more implicit assumptions when we construct the IPW estimator. First, we assume the population means are known or they are zero. Second, we pretend to know the probability pi. In reality, we have to estimate these parameters, but given the time, I won't go into details, but we can still guarantee the convergence rate while relaxing these implicit assumptions. So this is the main theorem in this paper, and this may not look very friendly at the first glance, but what it basically means is that if you have sample larger than dimension p by this amount, then the IPW estimator satisfies the convergence rate by square root log p over n in terms of the element-wise maximum norm. Also, this theorem has a natural interpretation that if you have more missing in your data, then the upper bound gets larger. Also, it could be hard to see from this inequality how the sample size changes, but basically you need more samples if you have more missing in your data set. The proof of this theorem is based on the element-wise concentration inequality. Also, the matrix norm can be controlled by a union bound argument. Okay, so we know that the IPW estimator satisfies this convergence rate square root log p over n. Then why is this rate so important? One of the answers is that we can use it in estimation of sparse precision matrix. Let's assume we are interested in estimating sparse precision matrix, especially when there is missing data. Then I'm going to plug in the IPW estimator in graphical lasso problem, and then we get the final graphical lasso solution. It is known that this solution satisfies the optimal convergence rate if the plugged-in estimator satisfies this convergence rate. This is also the case for other methods such as climb or graphical tangent accelerator. This is why we were so obsessed with this convergence rate square root log p over n. So now I'm going to talk about how the IPW estimator is practical compared to other methods. The missing imputation is a general way to handle missing data. Let's say we have m by p incomplete data matrix Y. Then by using the imputation methods, we replace the missing values with estimated values. And then it creates the pseudo-complete data matrix X. And based on this, we can compute the sample covariance matrix, and then we plug in this matrix into other estimation procedures, such as graphical lasso. Or alternatively, we can just plug in the IPW estimator in graphical lasso problem, and then we can get the sparse precision matrix estimator. So in this simulation study, we are going to compare these two precision matrix estimators, and these are the imputation methods that I used in this simulation study, and they are commonly used in practice. To measure the performance, we check how much the graph structure is recovered by computing the true positive rate and false positive rate. Finally, we compare the AUC values by using the ROC curves. The red box plots are the AUC values from the IPW estimator, and they are all greater than other imputation methods under different graph structure and different missing proportions. So this simulation study implies that the IPW estimator is not only theoretically grounded, but also empirically works well. So wrap up, we extended the missing dependency and we compute the IPW estimator, and we proved the optimal convergence rate of this estimator and use it in estimation of sparse separation matrix. So finally, this paper is online available at this archive webpage. And thanks for listening to my presentation.